Welcome to the structure analysis class. So if you recall, last module we have started the theory of failure. So we discussed different types of theory of failures. Total the 5 theories of failures available. So maximum principal stress theory, failure theory, maximum principal strain failure theory, maximum shear stress failure theory. All these theories we have discussed in the past lectures. So in this lecture today we will be focusing on the maximum strain energy theory. So let's get started. So this maximum strain energy theory is also called Hedge theory. So what this theory tells, the failure of the material will occur when the total strain energy per unit volume in the material reaches the strain energy per unit volume of the material at the elastic limit in simple tension. So what it says? So it says that, so for example, you consider a simply supported beam. So this is a simply supported beam. One hand is hinged, another hand is fixed, and maybe some load is acting on it. So because of the application of this load, external load, there will be deflection. There will be small deflection in the beam. So this is our beam, and there will, because of this P load, there will be small deflection in the load, deflection in the beam. So maximum strain energy tells that, so each material, maybe this beam is made up of steel, for example. So whatever material is made up of, so each material will have some maximum strain it can take. So each material can take some maximum strain. Beyond that, material will fail. So the load is applied, P load is applied into the beam, and because of that, there will be small deflection in the beam. So maximum strain in a beam will be, if it is less than the maximum capacity of the material, then our structure is safe. For example, the strain here is maybe 0.001, whereas steel can take maximum, maybe steel can take maximum 0.002, whereas applied strain is 0.001. So in that case, our material will be safe, right? So as long as our strain is less than the maximum limiting strain of the particular material, then our material will be safe, or the structure will be safe. So that says in this theory, failure theory. So if I draw the stress plane, so stress plane, if you remember, we have drawn maximum principal stress theory, means that failure plane. So that was rectangular. Similarly, maximum principal strain theory, that also we have drawn. If you have seen that, that is some trapezoidal shape, or maybe parallelogram shape. But this is the failure plane for the maximum strain energy theory. So it will be in a simply parabolic shape. So basically, in this theory, we have to compute whatever strain energy is done by the external load, and then we have to compute whatever is the maximum strain energy is there for the beam. So if this beam is made up of steel, then steel can take maximum some amount of strain energy. So if the applied load is more, the work done because of the applied load, or the strain energy because of the applied load is more than the capacity of the material, then our structure will fail, or the material will fail. So that is the this theory. So now we will derive our basic equations for the strain energy. So before starting into derivation, let's understand the basic of the strain energy part. So for example, we'll just consider it, this is a steel bar which is maybe hanged in a roof. So this is a steel bar which is suspended in a roof. And now you started gradually applying a load here, tension force at P. So at the very beginning, the length was, so the load P is applied gradually. So the length, maybe originally the length, this length is L. But after application of this load P, now the bar little bit elongated. So this is the elongated bar. So you are applying still load P, and the length has increased now. So increased length is delta L. So as per the strain energy, or the strain energy is basically work done by the load. So we'll just write it down, work done by the load. So how much work done by this load? So this will be basically half into load. Load is P into how much elongation takes place. So this how much extra elongated, that is delta L. So that is the work done by the load, and that we call it strain energy, SE. If you just remember, this is strain energy, SE. So the total strain or total work done by the force will be half into P into delta L. So that is the total work done. This work done will be stored inside this material as a strain energy. So let's draw a diagram quickly. So if I plot stress versus strain diagram of this experiment, so this is your strain axis epsilon, this is your stress axis sigma. So what will happen? So this load gradually we are increasing, right? Not at a stress. Gradually we are increasing load means the total stress will be gradually increasing and strain also gradually increasing. So after certain point, this is a stress strain curve. This is a stress strain curve of this experiment. So how much total work done by the force will be simply area under this curve. So this is the area under this stress strain curve is basically how much work done by the force. So that area is basically we denote it half into P into delta L. So that is the work done, strain energy. So that is written here also. If you see, uh, we have stated that the strain energy in a body is equal to the work done by the load P, so which is equal to half into P into delta L. So this is the total work done by the load P on a structure. So, so that we call it, that's the work done, we call it strain energy of a body. So next time whenever you heard about strain energy, please always you remember strain energy is nothing but the work done by the load P, that we call it strain energy. So strain energy U equal to now half into P into delta L. I hope this is clear. So now P is what? P is the total load. So if we just replace sigma, if you remember we discussed, sigma is equal to what? Stress equal to force by area, right? Then what is P then now? P can be written as sigma A, right? P can be written as sigma A. So that was written here. So P is written now as a sigma into A. P is replaced with sigma into A. And what is delta L? So sigma we can written P by A, so P is sigma A. But what is delta L? So we have written Poisson's ratio, if you remember, not Poisson's ratio, we strain. E is a strain, right? Strain is what? Change in length delta L by the original length L. So that we call it strain, right? So if you just find out what is delta L will be strain into L. So delta L is strain into L. Just replace P as a sigma into A based on this equation, and similarly delta L you replace it with strain into L. So this is the we just replace. Now if you simplify, what will you get? Half into sigma into E into A into L. What is A into L? So A into L is nothing but the volume of the body. So this body, if you see, A is the cross-sectional area of this steel bar, whereas L is the total length. So what is the volume? So AL will be the volume, right? Cross-sectional area into length. You will get it volume. So AL is replaced now with volume. So what we got, our final expression is half into stress sigma into strain into volume. So that is the total strain energy stored in any material. So that is the expression for that, right? So now if I write strain energy per unit volume, then you simply divide this strain energy by the volume. So you will get, that is the expression, half into stress into strain is nothing but the strain energy per unit volume. So that's what we derived also if you see this diagram. So what is the area? What is the area of this curve? It is simply triangle, right? Half into base into height, area of the triangle. So half into base is epsilon, height is sigma. So half into stress into strain is basically strain energy per unit volume. So this is the expression. So now again in the last lecture, if you remember, we have expressed strain energy into, this is the expression, right? Strain energy in terms of modulus of elasticity and the Poisson's ratio. We have derived how we got this expression we discussed in the last lecture. So similarly for three directions, so this expression we derived for the general case. But for any three-dimensional body, you have three axes, right? Three principal stress, sigma 1, sigma 2, sigma 3, whereas corresponding to you have the three principal strain also, epsilon 1, epsilon 2, epsilon 3, right? So we can write three epsilons in terms of principal stresses. So epsilon 1 equal to sigma 1, this expression we know, last class we have expressed, we have derived this expression. Similarly for three directions, three strains we have derived. So now this is our general equation. So in this strain energy equation, just replace sigma 1. So this is sigma and epsilon, right? So for three-dimensional case, what will happen? I'll just do it here. So this is the expression, general expression. So now for three direction where you have sigma 1, sigma 2 and sigma 3, right? Three principal stress corresponding to three principal strain, sigma 1, sigma 2 and sigma 3. So in that case, what will be the strain energy U? Strain energy U will be half of sigma 1 epsilon 1 plus half of sigma 2 epsilon 2, right, plus half of sigma 3 epsilon 3. So this is the total strain energy for a three-dimensional body U. So that's what we have written here. Here U equal to strain energy. Just now whatever we have written here, sigma 1 plus into epsilon 1 plus sigma 2 epsilon 2 plus sigma 3 epsilon 3. This is the total strain energy for any 3D structure. So now you replace sigma 1 value, epsilon 1 value, this is the epsilon 1 value we derived. So just replace epsilon 1 value, this one, epsilon 2 value with this expression, and epsilon 3 value with this expression, this three expression. And now after that, if you simplify the entire equation, you will get it 1 by 2e into sigma 1 square plus sigma 2 square plus sigma 3 square plus minus, this is the expression. So this is the total strain energy per unit volume in a three-dimensional system where sigma 1, sigma 2, sigma 3 are the three principal stresses and sigma 1, sigma 2, sigma 3 are the three principal strains. So this is the total expression for the strain energy, which is applied strain. So now another thing is the strain energy for the material, right? For the failure, we have two strain energy. One is whatever the capacity of the material, and next one is the how much is the applied strain energy. So this is whatever we derive, that is the applied strain energy of a body. Now what is the capacity strain energy? Means how much maximum strain energy the material can take. So that will be expressed into half into sigma t star into epsilon t star. What is sigma t star and epsilon t star? So for example, this material, made up of a steel, right? So maybe if this material is made up of Fe415 grade of steel, then the stress of this material is 415 Newton per mm square, right? So in that case, so total strain energy this material can take will be half into yield stress into yield strain, right? Same expression we have used. If you see the same expression we have used, but here maximum stress is how much this grade of steel can take. That is, for example, here if it is Fe415, then sigma t will be 415. So sigma t will be 415. Similarly, epsilon t is the strain due to sigma t. So this is the capacity of the material. To just simplify it, say epsilon t, you replace it with modulus of elasticity, right? So stress by strain is equal to E. So strain equal to stress by E. Just replace we have used this expression and we replaced this and we got ultimately 1 by 2E into sigma t star square. So this one is the capacity of the material, and whereas this one is the applied strain. So as long as applied strain is less than the capacity of the material, our structure is safe, right? That is the based on the strain energy theory. So as long as this value is higher compared to this value, our structure is safe. So that is our strain energy theory says. So for the failure of the material, this applied, whatever we derived in the last slide, this is one. So if this applied strain energy is greater than the capacity of the strain energy, then only the failure of the material will occur. So just you cancel it out 1 by 2e, 1 by 2e, and this is the final simplified expression for the strain energy. So this expression we have derived based on the three-dimensional body. So you have the sigma 1, it's the sigma 1, sigma 2 and sigma 3. But in two-dimensional case, you don't have the third dimension. Epsilon 3 won't, sigma 3 won't be there. If you replace sigma 3 with 0 for the two-dimensional body, so this will be our final expression. So if you remember, we expressed last class also that sigma t is what? Yield strength of the material. So, but in our design purpose, in actual design, we won't consider sigma t as our yield strength. So we divide sigma t by some factor of safety, and that sigma t we consider it as a permissible stress. So our design will be considered based on the sigma t, not sigma t star. So sigma t star will be the yield strength of the material. So if you use Fe415, so if you use Fe415 grade of steel, if you use this grade of steel, then sigma t star will be sigma t star is basically 415. But for the design purpose, we won't take 415. We take sigma t. Sigma t is which is actually 415 by factor of safety. So this factor of safety, if it is 2, depending on the different country, different factor of safety they are using. For India, we sometimes use 1.5 as a steel, or maybe 2 also. So if you divide it by 2, it will come as 207.5, right? So to design a structure, we considered our strength of the material is 207.5, this much, not 415. So we use permissible strength instead of yield strength in our design purpose. So sigma t is basically sigma t star by the factor of safety. So just replace sigma t star with sigma t, you will get this is our final expression. So if you remove the greater than equal to symbol with equal to, just replace it and you will get this is our final expression. So as long as this value is equal to sigma t, our structure is safe. If this value is greater than sigma t, our structure collapsed. So that is the theory for the maximum strain energy. So let's solve a quick example, then the problem will be uh, clear to you guys. So the question I have taken same problem. So if you see the same problem we have derived in last two failure theories also. So the principal stress at a point in an elastic material is given to us 200 Newton per mm square, which is a tensile, and 100 Newton also tensile, and 50 Newton per mm square, which is compressive. So it is a three-dimensional body. Three principal stress is given to us: sigma 1 200, sigma 2 50, and sigma 3 is sigma 1 is 200, sigma 2 is 100, and sigma 3 is minus 50 because sigma 3 is a compression, right? So if the stress at a elastic limit in a simple tension is 200 given, so sigma t star value is given. The material of the steel, if the material is made up of steel, then the strength of the steel is given. Sigma t star 200 Newton per mm square. Determine whether the failure of the material will occur based on the maximum strain energy theory. So that is a very simple question. So let's solve it quickly. So sigma 1 is given to us 200, sigma 2 also given 100, and sigma 3 is 550, which is basically minus 50 because it is compression. And Poisson's ratio also given to us mu, that is 0.3. Elastic limit in simple tension sigma t star given 200 Newton per mm square. So now total strain energy of a body will be how much? So this is the total strain energy per unit volume in a material is this is the expression, right? So this expression we have derived in the last slide. If you just recall and if you see just the last slide, you will see this is the expression we have derived. So now just plug in the values. So 1 by 2 e into sigma 1 value is 200, sigma 2 is 100, and sigma 3 is minus 50. Similarly, 2 into Poisson's ratio is given to us 0.3. Sigma 1, sigma 2, all the values we plug in and you compute whatever is the total strain energy. So once you compute, you will get total strain energy is 1 by 2e into 49,500. So this is a total strain energy developed because of the principal stress applied to the body, right? This is the applied strain energy. Now we have to compute what is the capacity strain energy, how much strain energy that material can take. If the material can take more strain energy than this one, then our structure is safe. Our material won't fail. So let's compute how much is the strength of the material. So the strain energy per unit volume correspond to the stress at the elastic limit in a simple tension is given by. So this is the expression. Last slide, if you see, we have derived this expression. So 1 by 2E into sigma T star square. So this is the expression, is the capacity of the material. So just replace it. Sigma T star value is given to us 200. Just replace 200 with it, and this is the final expression. So that much strain energy our material can sustain, 40,000 by 2E. So that much material strain energy our material can take. How much is applied then? So applied is 1 by 2E into 4950. So 49,500 by 2E is applied, whereas our capacity is 40,000. So our capacity is less, right? And the applied share strain energy, sorry, strain energy is more. So the material will definitely fail because your capacity is less and the applied strain, applied applied strain energy is very high. So as per this theory, our material will fail. So just using these equations we have derived in the last slide, using the strain energy equations, we can easily compute whatever strain energy is developed because of the load and how much is the capacity. If capacity is more than the applied strain energy, then our structure is safe. If it is more, then our structure will fail. So that's what we have solved a simple problem using this theory. Thank you.